we are going to study topic that is data structures and algorithm. So data structure, we will look into two angles. One is data, other one is information. Okay. As an example, if you take value 30, it's a raw data. Okay. And if we associate this 30 to age of a person or something else, then that becomes an information. So basically, the information is the processed data. Okay. And when you store something on the memory, we have to locate that value, and that is called the search operation. Okay. Once you locate the data, we can retrieve the value, and that is what we call the retrieve operation. And once the data has been retrieved, we can process the data, and that is what we call the information. And after processing, again we can store it back to the memory, which we call the storage. Okay. So any data structure, if you take that data structure, will be having three operations. That is search operation, that is to locate the data, and store operation, this is to store back the value. Okay. And retrieve operation, that is what are the data we located, we have to get it for our application. So that is the retrieve operation, right? Now, there are two components. If you take a data structure, there are two components. One is called data, and other one is called operations. Okay, so data is normally the raw data, something like what we mentioned earlier. Okay, so only raw data, and there are certain operations that we use it for those data, but there will be some specified manners. So that varies from data structure to data structure. Okay, now when we combine these two things, and these two things together only called a data structure. Okay, the data structure is not just like a structure where we are storing the data. No, it is not like that. It is having two components. One is the data. So there we consider some organized manner. Therein we store the raw data, and to operate, I mean, what we have to do, something like that. So there are set of operations. Okay. So these two together combined only called the data structure. And if we combine it and represent it, and that is called the structural representation. Structural representation. Okay. So this is what we consider. Now, when you take this data, how we store that? Because sometimes some application that may need a lot of data. For example, here we mentioned that is only one value. So for example, if you take a student data, the data consists of several things, right? Name of the student, age of the student, class which he is studying, mark he obtained, all the things will be there. So these things together only a data corresponding to one entity, right? Therefore, sometimes the data may not be very simple. It may be a little complicated. So okay, whatever it may be. So here we have a storage mechanism. So in the storage mechanism, we will store the data. Okay, basically what it is doing is it is bringing the conceptual boundary. We mentioned that data structure will be having two components. One is data, other one is operations that act upon the data. So these two together called the structural representation. And basically what it provides is it provides conceptual boundary. Okay, conceptual boundary. I think I don't know whether you have studied object-oriented programming or not. So if you have studied object-oriented program, you will be knowing that. Okay. So every class will be having set of variables. There we consider for storing the data. Then there are some operations, right? The functions, member functions will be there. So these two things together only encapsulated and put into one class, right? Then from the class we create object, something like that. Okay, but what happens is not all programming language that supports that. For example, if you take a C language or Pascal, so that kind of concept is not there. So here what we are doing is we are trying to bring a structural representation so that when we execute something on the data structure, it cannot violate, or it cannot damage the data. Okay, so there we are mentioning a conceptual boundary for that. We are mentioning a conceptual boundary. Why we really needed is, as an example, I can say that okay, suppose you take a vector. Okay, so vector contains so many values. Maybe each of the value will be an integer. Okay, and if you say that vector of size n means there are n such values available, and if you want to do a vector addition, okay, if you want to do a vector addition, so vector addition is different from normal integer addition. So you cannot make use of the normal integer addition for that, because you may add one value or two value, but you may leave out the remaining. So vector addition means whole vector to be taken into consideration, and whatever we are doing the addition, vector addition, that to be performed. So how we do that? So that will be done in the operations. Okay, so we have a functions, so that are being defined. Okay, what kind of operations to be carried out? So that will be there. So this is one example. Second example is later on we will study a data structure called the stack. So this is not a very difficult data structure. So stack means, for example, if you take a set of coins, what you do? You keep a coin one over the other, right? So this is called a stack. This is one example of stack. So suppose you have 10 coins. What do? You put one coin on the top of that another coin, then on the top of the other, like that 10 coin you put that. Suppose you want to take one coin, and you assume that these things are being put inside one small cylinder where the coin can fit. Okay. So if you do like that, if you want to remove a coin, what you can do? The coin which you inserted last, that can be taken out first, right? The coin which you have inserted last, that can be taken out first. So this is basically a structure of a stack. Okay, now if you want to implement that stack, then what you can do? You can make use of an array. For example, I can say that there is an array here. I can put an element, one element here, another element here, like that. Okay, so I can put the element. So if you do that, if you consider this is a stack, then the element which I inserted last to be removed. But what happens in the programming sense, if you look at, this is basically an array, right? This is basically an array. We assume that this is having 5 elements. This is A here, B here, C, D, E, like that. There are 5 elements available. So once you consider this as an array will be having an index, right? So you can say that this is the first one, second index, third, fourth, fifth, like that. So if it is an array, what you can do? And the name of the array is yes. Okay, we assume that name of the array is yes. Then you can always use the thing that S of 3. So if you say S of 3, so that means you can say R is equal to S of 3. Then what happens? The value C will be coming here. So this is not a permissible operation for the stack. So permissible operation for the stack is element which we inserted last, that to be taken out, not from the middle. But if you deal as an array, you can take it from the middle. So what we are trying to do is, if you define this as a data structure, then data structure, as I mentioned earlier, there are two components. One is called data, other one is called the operation. Okay. So now here the operation, we will define clearly that what it has to do that. For example, if you want to remove operation is there. So the removal operation will remove only the topmost elements. It cannot remove from the middle. So we can make a conceptual boundary. So it means we can create a condition. Okay. Then second thing is, when you talk, there are a lot of things we have to discuss here. Okay. When we talk about data, so data can be stored in different form, right? Different form. So I can store it in the form of an array, or I can store it in the form of a tree-like structure or a graph-like structure, something like that. The question is what storage representation I consider. Okay, so that we may have a doubt. So this is based on two parameters. So that the parameters are called time and space. Okay, so there are two parameters. One is called time, and the other one is called space. So based on these two parameters only we consider, and the best time and limit, less space which you use, that we say that efficient. Okay, so these two terms actually refer to the efficiency of the data structure. Okay, so efficiency of the data structure is based on the time and the space. So what we mean by time here? So for example, I stored something into the data structure. Okay, and I want to retrieve that. So retrieve, if you want to retrieve, I have to execute an operation. Okay, here. So if I execute an operation, the execution time is there, right? So that is what the time we mean that. So if the time is large, it is not efficient. If the time is less, it is efficient, right? Okay, so the time is a factor that denoted with the execution of the various operation. Space is related to the storage that we consider. Sometimes some data such as, if you want, some set of data you want to store in a data structure, it may take more space, but we have to see that it has to take less space as possible. Okay, so this is what we consider. Then next thing is data type. Sorry. So next thing is data type. So you have studied some data types, concept of data types in the programming language, even in C also. So int, float, double. So these are all called the data type. Okay. And here we have studied some introduction about a data structure. So what's the difference between these two? For example, if you take C programming, you can say that integer. Then if you say a comma b, then what it means? So a is an integer, b is an integer. It's an integer variable, right? So in this integer variable, you can store the integer value. Okay, like that. So the int is called the data type. So in the data structure, what happens is, suppose I define a data structure called vector. Okay, this data structure is required for storing a vector. But I may have to store so many vectors, right? We have to store so many vectors. So something like that. Here, when I want to store two integers, I have declared two things, int a comma b. For a, we can store one integer, and b, we can store another integer. Like that, in the data structure also, if you have given a data structure, for example, for the vector, I may need to store several such vectors. Therefore, we have to create the objects. Why I want that? Because not all such things are not being defined in the built-in data type. So these are all built-in data type available in the program. Sometimes user-defined data type, that is also needed based on our application. Okay, but that will be of different thing that may not be available. So in that case, I should create objects, something like what I have done here. The question is whether it is possible or not possible. It is always possible. Okay, and therefore these data structures are basically called user-defined data type. It can be considered as a user-defined data type. Okay, so we can have a structural representation that consists of storage as well as operations that act upon the data. Okay, then later on, any number of objects to be created out of that we can create. Therefore, something like what we see in the programming language, like data type, here the data structures can also be considered as a data type, but this is what user created, and hence we may say that it's a user defined data type. Okay. Okay. Now, once you think about this data type and data structure, there are two thoughts we get that. One is called the logical view. That is a logical view of the data structure. And the other one is called the physical view. So these are the two thoughts. So the logical view is called abstract data type. Logical view is called abstract data type. Already I mentioned that the data structure can be considered as a user-defined data type. Okay. Here we are giving a specific name that is called abstract data type. So logically, if you see a data structure, it is called abstract data type. Why we say it's abstract data type? So we should know that what it is rather than how it is. For example, I am driving a car. I should know how to drive the car, but there is no need to know about the internal circuits or mechanics that is available, right? So I am bothered about what it is rather than how it is. How it works, no need. But how to operate, if I know, that is sufficient to drive the car. So therefore, my view is a logical view. It's abstract. It's abstract. Okay. Similarly, if you have a TV, you are operating the TV. What you know that once you press this button, one button, then what function the TV does. But we do not know how the circuit are being defined. So once again, that is abstract. It's a mathematical model. Basically, it is a mathematical model that gives set of utilities, okay, without any implementation details. Okay, without any implementation details. So that is what called the abstract. So here also the data structure in the logical view, we consider that as an abstract data type. That means as far as the user is concerned, user knows that for this data structure, these are the operations that can be performed. Okay. And once they know that, they can just call the operation. But how the operation execute, there is, there may be some programming code or implementation details will be there, but the end user need not know about it. Okay. So that is called the logical view. And another thing is called the physical view. So in the physical view, actual implementation will be considered. The physical view, actual implementation will be considered. There you should know that how it can be carried out. So in the one example I mentioned earlier, that is called the stack. So for the stack, there are two operations, that is push operation and pop operation. Push means we can push one element on the top of the stack. Pop means we can take the topmost element out. So these are the only two operations. So end user is supposed to know that if they are making use of the stack object, okay, these are the two operations are permissible. Push and pop. Push will push the element and pop will remove the element. So this is what they're supposed to know. So the logical view, it's only abstract. But if they want the physical view, they should know how this push can be carried out. So if you want to push that, you should know that what was the previous top. On the top of that, we have to insert the element, something like that. So a lot of other details that may be needed. So here what happens is we are having two thoughts. One is the logical view, other one is called physical view. Okay. Now, you see here several terminologies we have studied, and if you have any doubt, you can ask. We can, I can clarify. So it is better to know that. Even otherwise also, you can see the video once again, or you can go through the notes, and if you have doubt, you can clarify. Okay. So these are some confusing terms. Later on, people feel that even after finishing their degree, they still have a doubt. So that's why I'm giving more detail about all this. Okay, here two things we have studied. One is called data type. So this one, okay. Other one is ADT. So now in the data type itself, two things we have considered. One is data type, other one is called the ADT. So what's the difference between these two? Okay, the data type is actually the implementation or computer representation of ADT. Okay, we can say that implementation or computer representation of ADT. So that is called data type. So I can give one small example for this. If you say integer, okay, if you say integer, so it's abstract data type. Why? You say integer, it's abstract data type. Why? But in the programming language, I am not saying abstract data type, I am saying data type, right? I am not using the word abstract data type there. So if we say integer, it's abstract data type. The reason is, you know that if you have two integers, the two integers can be added, two integers can be multiplied or subtracted, or one integer can be divided by another integer. So these are the top level operations that you are doing that, right? So with the set of integers you have, what you can do that you know. So it's abstract data type. Now the integer, what it does that you know. Now for that integer, if you take it the programming language, then why that int? Okay. For example, in the C language, int, why we are not saying it's abstract data type? Because the integer what you had in the abstract level, that is abstract data type, there you can consider int or signed int like that, okay, signed int or long int like that. So there are several forms. So the several forms varies depending on the implementation, right? Okay, the representation of the signed int while implementing will be different compared to the integer, because signed int should say that it's a positive or negative like that, but that is not there in the int. So here it is based on the implementation. Okay, this is based on the implementation. Therefore, when you say it's an integer, it's abstract data type. And when you say int, signed int, long int like that, then that is called a data type. Therefore, we say here that data type is a implementation or computer representation of ADT. You got it? Okay. So this is the difference. Therefore, in our data structure, we consider data structure in the logical view as abstract data type. Okay, abstract data type. Therefore, once you implement it in the system, that becomes the data type. That becomes the data type. Once it becomes the data type, you can create any number of objects, and each object will behave for that particular data structure. Okay, so later on when you start doing that, you will be knowing that when you do practicals and other things, you will be getting more clarity. Okay, do you have any doubt till now? If you have any question, you can ask now, so we can clarify and go further. Okay, I think all of you understood. Can I assume that way?
Yes, sir.
Yes, sir.
Okay. Now, I think in your computer fundamental course, probably before writing the program, you might have asked to write algorithms or flow charts, something like, right? Algorithms, then you have to go to lab and write the program. So we have two things, algorithm and other one is called the program. We might have seen that, okay, even you might have noticed it. Some people, they write the algorithm using programming language. It's correct only, nothing wrong. Algorithm can be written in any way. Even flowchart is also an algorithm. You are describing that how step by step it goes, right? Flowchart or any pseudo language, you can write that. Or you can make use of any programming language. Using that, you can write the algorithm. So if you say a programming language can be used for writing the algorithm, then can I say the program and algorithm are same or not? Okay, the question is coming, right? Whether I can say program as an algorithm or algorithm as a program, whether these two are same or not, the question is coming, right? So actually this is not same. The program is based on certain syntax, okay, defined for the program language we are writing. Okay, algorithm, there is no syntax, so it doesn't matter. But algorithm is having certain specified properties. Then only we say that it's algorithm. And some of the very important properties the algorithm is supposed to satisfy is, one is called definiteness. Definiteness. So definiteness in the sense that unambiguity. So whatever the instructions you are doing, how you write the algorithm? Algorithm is a set of instructions you execute one after another. Okay, maybe there are 5 instructions there, one, then next one, then some if condition there, based on if condition something or else condition something like that. So these are all instructions. These instructions maybe it may be an addition, or it may be a subtraction, or it may be a sorting or something like that. So these instructions should be unambiguous. Ambiguity should not be there. Then that is called definiteness. So when you write the algorithm, whatever the operation or instructions, whatever the instructions that you are writing, that should be unambiguous. This is the first property. Then second property, okay, there are a few more things are there, but very important thing only I am pointing out. That is called effectiveness. Effectiveness. This is basic in principle and feasible to carry out. So that means if you write some instruction, the instruction should not be very complicated or anything. Okay. So this should be basic in principle and feasible to carry out. So that is called effectiveness. So what are the instructions you are writing that should be very effective? So that's what we mean here. And one more property there that is very, very important. If that property is not satisfied, then you cannot state that as an algorithm. That is called finiteness. Finiteness. So this property, based on this property, you will study a lot of things in other subjects later on. Okay, so finiteness. What do we mean by finiteness here? That is, if you write the algorithm should terminate after finite amount of time. Remember, after finite amount. We are not simply saying this stop. So once you write the algorithm should terminate after finite amount. How algorithm will terminate? So it's only abstract. Okay, it's only it has not been implemented, even maybe in the pseudocode. But if you execute, if you implement and execute, that will happen, right? So that theoretically also you can look at. Theoretically also you can look at, right? So the finiteness property, that is very, very important. Okay. So if the finiteness property is not there, then we cannot say that it is an algorithm. So one small example again I can do that. I take a program in a C program. Okay, let us take C program. I write a main function. Okay, I write a main function. In the main function, I can write a statement for semicolon, semicolon, then semicolon, then I close the main function. This is my main function. So this is my C program. Can I say this is a program? That's my first question. Can I say this is a program? Yes or no? Is it a program or not? Are you there? If you are not there, I will stop recording. Is it a program or not?
Sir.
Pardon?
It's a program, sir.
It's a program. Why you say it's a program? It's a program only. Why you say it's a program? Because it satisfies the syntax. Everything is there, right? The syntax, everything followed. If you compile the program, there will not be any error. And if you run the program will run, right? But can you say this is an algorithm? You cannot. Why? Because this program won't terminate. This is an infinite loop, right? If I run this program, the program will keep on running. It never stops. So that means it is not having finiteness property. Okay, it is not having finiteness property, and hence this is a program but not an algorithm. So now you understood the difference between the program and an algorithm. Okay. Now when you study the algorithm, there are three things we study. Okay, so later on we will see deep into this. So first of all, I am giving an overall view of what this course is. Okay. Now when you study an algorithm, there are three things we have to consider. One is called design, other one is called correctness, and the third one is called analysis. So what is the design? So there are several design techniques available. For example, divide and conquer, greedy, then dynamic programming, backtracking, branch and bound, heuristic. So many, okay, so many design techniques are available. So not all techniques are useful for all problems. Certain problems, certain techniques are useful. So we have to identify that, and accordingly we have to design the algorithm for that particular problem. This is the first step. Then second thing is, so you have done the design part. You should know whatever you have done is correct or not, right? How do you find whether it is correct or not? You cannot implement and check, right? You cannot implement check. So this is what you generally do, but that is not the thing. That is not possible. Sometimes it may be a bigger thing. So before going for implementation, you have to check the correctness. How you check? Mathematically. Okay. You have to check the correctness mathematically. Anyway, I can take one example and illustrate that so that you get the idea. So there are several mathematical proof techniques are available. Okay. And out of it, some techniques will be useful for proving the correctness. So mathematically, we say that if I run this algorithm, the algorithm will give the answer correctly. This is what I have to do mathematically. If I prove the correctness, then whatever the instance you give, algorithm will give the correct answer. So that particular part, the part in which Mathematically, you are trying to prove the correctness. That is called the proof of correctness. Okay, the correctness part. So first we design the algorithm. Then whatever we have designed, we proved that correctness is there. Then what else we need? So we have to look for the efficiency. I already mentioned that the efficiency can be determined based on two things. One is called the time factor, other one is called the space factor. So that is what we call the analysis. We are trying to analyze our algorithm, that how much time the algorithm will take if I execute. I am not practically putting the algorithm into the system and execute. No. I have only theoretical representation. My algorithm is only on the paper, which I have written using my pen, which I cannot run, right? So with that algorithm, I have to say that if I run this algorithm, how much time will take? That is without actually implementing. So this is theoretical analysis. This is a theoretical analysis. Okay, so this is a time analysis. And similarly, if I want to run this algorithm, how much storage space I need it? Okay, so these are the two factors we consider. One is called time, other one is called space. So the analyzing the time and space, that part is called the analysis part. Okay, one example I can take. Then after that I can stop the class. For example, you assume that you have an array of size n. That means there are n elements available. Maybe the array index 1, 2, 3, etc. up to n. Here we assume that some values are being stored. You can even assume that some integer values are being stored. Our problem is like this. Given an array of n values, we have to find the largest value available in the array. Okay, we have to find the largest value available in the array. So how you write the algorithm? So maybe I can give a name. So first the design part, right? First the design part. So in the design part, I am giving a name that is called maximum. Maybe maximum name. And array name, let us say A. And there are n elements. Array name is A and there are n elements. So this is the name of the algorithm. In that, what we want to find the maximum value. Let me take one variable, that is m. So m will be considered as the first value, a of 1. So I take this value. Okay, that I assume that it's the current, this is not 0, so some value available, right? So that I assign to m. Then there are remaining n-1 positions available. I will compare the current m value with the remaining, and if I find or if any larger value encountered there, then I will modify this m value. So what should I do? I have to consider remaining n-1 value. So I have to put a for loop for I is equal to 2. 1 already considered, right? 2 to n 2. Therein, if a of 2 is greater than the current m. Okay, a of 2 is greater than the current m. Then, so this is algorithmic code, not the C programming or anything, right? So this is algorithmic code. So if a of 2 greater than m, then, so we got a larger element, right, than m. So we have to modify this m as a of 2. Otherwise, we won't do anything. And this will be continued. If the element is lesser, nothing will be carried out. So it will move to the next position, something like. So once we reach the final position, whatever the largest value, that will be available again. And that value we will return. Okay, return it. So this is our algorithm. So design part is over. Okay, the design part is over. Now I have to prove mathematically that this algorithm will always give the maximum among m elements available in the array. Mathematically, I have to prove it. Okay. So I am going to write a theorem. Okay. I am going to write a theorem. So the statement of the theorem is the algorithm. So name of the algorithm is max, right? So this is the name of the algorithm. So algorithm max will always returns the maximum value. Maximum value. So this is my theorem statement. Okay, now the proof. Okay, theoretically I got to prove that it will give the maximum value. So what the algorithm returns, that we do not know. Okay, we assume that the n elements are something like x1, x2, etc., xn. We can assume like that because these are all variable. We can give different values, right? So I am taking the values like that, x1, x1, x2, etc., like that. The actual value will be something different. Okay, it is something like variables. Out of that, let us assume that let the algorithm returns. So out of these n values, it will return one value, right? We are starting with the x1, then comparing with the remaining element, and whatever be the thing the algorithm finally having in the variable m, that will be returned, and we assume that the algorithm returns xi. If this xi is maximum, no problem, we proved. Okay, if this xi is maximum, it's proved, but we do not know. What we want to say that we have to tell that this xi is maximum. Whatever the algorithm returned, that is a maximum. Okay. Therefore, we are taking the proof technique that is called the proof by contradiction. There are several techniques available: mathematical induction, proof technique, proof by contradiction, then direct proof, like that. Several things are available. So in the proof by contradiction, we assume xi is not the maximum. So, and as contradiction, that is whatever the algorithm returned is not the correct one. It's not a maximum. So if this is not the maximum, some other element will be larger than that, no? Okay, there exists at least one element which is larger than this. If this is not maximum, there exists, that implies there exists j such that xj is, okay, xj is maximum. Okay, or we can say xj that is larger than xi. Okay, this also you can consider. So there exists a j such that xj is more than xi. But algorithm is supposed to give xi, but it is not giving xj, but it is giving xi. So here there are two cases. What is this I and j? I and j are the indices of the array, ith position and jth position. So there are two cases. One is this I can be less than j, case 1. Okay. Case 1 is I is less than j. That is xi is appearing before xj. Okay. Now if we look at this algorithm, okay, sorry. So if you look at this algorithm, in the if statement, what happens? If j is here, what happened? J is appearing after I. J is appearing after I. So once that j comes here, according to the if condition, that the value is larger, the condition if condition satisfies. As if condition satisfies, what happens? That larger value will be assigned to m. That value only be returned. So the possibility of returning xi is not at all possible. Okay, so that is a contradiction. So that means if I is less than j, this is the first case. Okay, therein, according to this if condition, the if condition gets satisfied in that case. As it is getting satisfied, the value of m would have been altered, and so returning xi is impossible. So that's a contradiction. Similarly, if I take another case is I is greater than j. So that means if j is appearing before I, if j is before I means the value of m is already assigned with j. Okay, the value of this xj is assigned with this m. And when the I comes later on, this if condition fails. If condition fails, the xi cannot be the m cannot be updated with xi. So that is also not possible. So whether this case or these are the only two cases possible. In both the cases, we get a contradiction, and against we can conclude that our assumption is wrong. What is our assumption? This is our assumption. Therefore, xi is always the maximum, and against our algorithm returns the correct answer. So this is what the mathematical proof. So this is the way the proof should be given for all algorithms. Once such a proof is given, whatever the instance you consider, no problem, the algorithm will always execute correctly. Okay, the third component, that is called analysis. Okay, once again, this particular example, let us consider analysis. First, we take the space. Okay, space. So here, how much space it takes? That is the number of variables and other things. Here, A is considered, right? Array A. What is that? So that contains n values. That contains n values. So at least we have to store n values, no? So space requirement is n for storing the array. Then another index that n is available. Okay. So that is n plus 1. Then one more variable, temporary variable we are using. So that is also plus 1, this m. And another variable I, this is also used extra variable. For that also we need a space, therefore that is 1. That's all, right? So this is our space requirement. So totally how much? N plus 3. So n plus 3 storage space required for running this algorithm. This is the space analysis. It's a very simple example. This is not, may not be simple in all the cases. Okay, only to make you understand, I have taken a small example and explaining it. That's all. And second component, that is time. Time. So every operation will take 1 unit of time. What is this one? We do not know. 1 unit of time, some unit. Okay. This is an assignment statement. It will take 1 unit. And this is a for loop. How many iterations this for loop does? N minus 1 times, because starting from 2, right? So n minus 1 iterations. But each iteration, 1 comparison and 1 assignment at the maximum. We will consider only maximum. Sometimes if this condition fails, we won't do the assignment. Okay, it's okay. But we have to consider the maximum possible. So maximum possible is all the time the updation that can happen, right? So that means here one comparison, one that is inside the for loop there are 2 units of time we are spending. Then returning, that is 1. So totally how much? N minus 1 plus 1 plus 2 and plus 1. So totally n plus 3, right? So this is our time requirement. But there are some notations available. So to represent the time, that and we will see later. So we have made a small mistake. No one noticed, but it's very simple. I thought you would have noticed. No one even pointed out. So either you are not concentrating on the class, or you may not be aware about that. Something. Okay. So the mistake what we have did is, so in this particular code, you see for I is equal to 2 to n do. Actually, this is not A2, A of I, right? This is A of I. So instead of putting I put 2, but no one pointed out. So you can make a note of that. This is A of I greater than M. Then only, as far as I changes, this also gets changed, right? Okay.